In lecture, we've been talking about the ideal gas law and the ideal gas constant R. And I mentioned in lecture that it's possible to measure R if you simply know the values of pressure, volume, moles, and temperature. So we're going to do a little demonstration today where we're going to measure R by taking a sample of air and determining P, V, N, and T so that we can calculate R. To hold our sample of air, we're going to use a syringe. We have a large syringe here, 140 milliliters, and we're going to collect about 100 milliliters of air. The syringe is graduated, and you'll see that in a moment when I take a closer view of it, so we can measure the volume of the air very easily. The pressure in the room, we're in Stockton at sea level, it's invariably 1 atmosphere. The temperature we can get from using a thermometer to measure the temperature of the room. The challenging part is determining the number of moles. How do we figure out how many moles of air are in a sample of air in this syringe? Well, we can't measure moles directly, so we're going to do it indirectly. We're going to use something we learned back in chapter 9, and that is converting grams into moles. We're going to weigh the air in this syringe using this very nice balance we have that weighs out to 1/1000th of a gram. And then knowing that the molar mass of air is 29 grams per mole, we can then convert the grams of air into moles. So we'll take the milliliters of air in the syringe and convert that to liters to get the volume. We know that the pressure in the room is just about exactly 1 atmosphere. We'll use a thermometer to measure the temperature. It feels like it's about maybe 20 degrees Celsius today, but we'll measure that, and then we'll convert that into Kelvin, and then we'll use our determination for the number of moles. We can rearrange the equation and calculate the value of R. So let's go ahead and start doing some measurements here. We'll move the camera in closer now so you'll be able to see what we're doing and to measure the values on the syringe and on the balance. Let's go ahead and take a closer look at the syringe we're going to be using to collect our sample of air. On the bottom of the syringe we have a stopcock. When it's in the vertical position, it's open, but if I turn it horizontal, it will seal off the syringe so that air cannot get in or out. When it's open, it's very easy to pull up the barrel of the syringe. We can raise this up and collect a sample of air. And we're going to collect a little over 100 milliliters for a very simple reason. We want to be able to lock the syringe in place, and there happens to be some nice little holes drilled in the syringe just at that 100 milliliter mark. So we're going to pull it up, and then we'll lock it in place with that Allen wrench. Now, the reason we need to lock it in place is very simple. As I said, it's easy to raise the plunger when the stopcock is open, but when it's closed, it becomes very difficult. If we close this off and we try to raise it up, it doesn't move because there's a vacuum in here. If we begin to pull that up, air can't get in, it leaves a vacuum behind. But there's lots of air pressure pushing down on that plunger. And I've calculated it's about 26 pounds of pressure, which means you need to pull up with 26 pounds of force to get that to come open. And it's going to want to slam back down, so I'm going to pull that thing up, slip that Allen wrench in there to keep it locked in place. The reason we want to do that is very simple. When we measured the volume of water, say in a graduated cylinder, the mass, we would weigh the cylinder empty, and then we would fill it with water, and we weigh it again to get the difference. So we'd start with an empty cylinder, and then a full cylinder. We're going to do the same thing here. In this case, because we're going to want to weigh this syringe empty, which means containing nothing, not even air. So we're going to pull that plunger up and basically fill the syringe with vacuum. We'll weigh it with nothing inside, and then we'll open this up and allow air to come in. We'll weigh it again, And the difference between the two will give us the mass of air in the syringe, and that of course is what we will use to calculate the value for N. So let's go ahead and get started. Let's begin by doing the easy part, which is measuring the mass of the syringe with air in it. So we'll go ahead and open up our stopcock, and let's raise this up till just over 100 milliliters so that we can use our Allen wrench to lock this in place. We'll turn this a little bit, there we go, it's a little simpler to lock it. So we can go ahead now and close the stopcock, and we have a sample of just over 100 milliliters of air. We'll go ahead and weigh that, and then we will come back and then seal the syringe and fill it with vacuum, so to speak, and we'll weigh it again, and the difference will give us the mass of air. So right now you can see that the volume in the syringe is about say 103 milliliters or so. So we'll use that as our volume of air. Let's go ahead now and get the mass. Because the amount of air that we're weighing is very small, we're going to use what's called a milligram balance that can weigh to the nearest thousandth of a gram. It looks like our mass is just about 81.166 grams. It fluctuates a little bit because of the air currents in the room, but it's probably plus or minus a thousandth of a gram. So we'll go with 81.166 grams as the mass of the air in the syringe. The most challenging part of this experiment is filling the syringe with vacuum and weighing it, because it takes quite a bit of force to pull that plunger out, and it's very helpful if one has an assistant to insert the Allen wrench into that hole. But since I don't have an assistant today, I've devised a method to do this myself. I've clamped the Allen wrench in this clamp, and I'm going to try to pull out the plunger and then lower it over the Allen wrench and lock it in place. So let's see if we can do that. We've got the stopcock closed. So I'm going to put that 26 pounds of force here and pull out that plunger. There we go. And let's see if we can line that up with the Allen wrench. There we have it. Worked beautifully. So now we have our syringe, and it's filled with vacuum, i.e. nothing. So all we have to do now is head over to the electronic balance, and we'll measure the mass of the empty syringe, match that up with the mass of the syringe full of air, and the difference between those two will give us the grams of air, and from that, of course, we can calculate the number of moles. Not surprisingly, the syringe filled with vacuum, so to speak, or empty, does weigh less than the syringe did filled with air. It looks like the mass is just about 81.046 grams. So we can subtract that from the mass of the syringe filled with air that we had measured earlier, and then we'll convert that final mass into moles, and we can plug that into the ideal gas law and solve for R. Now that we've measured our pressure, volume, moles, and temperature, let's go ahead and determine the value of R. We'll start out with the ideal gas law, and since we want to solve for R, let's go ahead and rearrange that, which gives us R equals PV over NT. So now we simply need to have those four values that we can plug in. Start with our pressure. As I'd mentioned earlier, the pressure at sea level in Stockton is usually just about 1 atmosphere. We can see here it's 759 millimeters, and since there's 760 millimeters of mercury in 1 atmosphere, this comes out to be almost exactly 1 atmosphere. For the volume, we simply use our syringe. It looks like it's probably closer to 102 milliliters, which would come out the same as 0.102 liters. To calculate the moles, we're going to use the masses that we measured. So here's the mass of the syringe filled with air, and this is the mass of the empty syringe filled with vacuum. We'll simply use the molar mass of air to convert the grams to moles, and that comes out to be 0.00414 moles. For temperature, we'll just take one of our laboratory thermometers, and as I suspected, the temperature in the lab is usually about 20 degrees Celsius, and that comes out to be 293 Kelvin. All we have to do now is simply plug in these values into our equation. So we'll plug in the pressure, volume, moles, and temperature in the appropriate units, and we get a value for R of 0.084. To see how well we did, let's compare that to the actual value of R. We'll take our experimental value of 0.084, subtract the actual value of 0.082, go ahead and divide it by that value, multiply by 100, and we get a percent error of just 2.4%. Well, it looks like our results came out pretty well. We got an R value within a few percent of the true value, and that's not bad considering the equipment we're using is pretty simple. So R may seem mysterious and complicated, but it's actually pretty simple as long as you make sure you use the correct units for pressure, volume, moles, and temperature. We can determine the value of R very accurately.